At this very moment, somewhere across the universe, a star is reaching the end of its life. Its death will not be quiet. Instead, it will explode with such tremendous force that for a brief time it can shine brighter than an entire galaxy. These enormous stars spend millions of years in a state of furious equilibrium, burning with incredible intensity. But eventually, that equilibrium fails. The star's own gravity overpowers everything else, compressing it into something so dense and so extreme that even light cannot break free. This is not a rare event. Across the observable universe, a massive star dies and collapses roughly once every second. That means, in the time it takes you to listen to this sentence, somewhere in the vast darkness of space, a star has just crossed the point of no return. Most of these cosmic deaths happen so far away that their light will never reach us. The observable universe extends for about 46 billion light-years in every direction. And within that immense volume, hundreds of billions of galaxies each contain hundreds of billions of stars. The sheer scale is almost impossible to comprehend. To put this in perspective, if you could count every star in the observable universe at a rate of 1 star per second, it would take you more than 3 trillion years to count them all. That is more than 200 times longer than the current age of the universe. And among all those stars, the massive ones, the ones capable of forming black holes, make up only a small fraction, perhaps 1 in every few hundred stars. Yet their impact on the cosmos is profound, far exceeding what their small numbers might suggest. Others occurred billions of years ago, and their final flash is only now arriving at Earth, a ghostly echo from a distant past. When we look at a supernova explosion today, we are quite literally looking back in time, seeing an event that happened when the universe was younger, when Earth did not yet exist, when the atoms that would one day form your body were still scattered across interstellar space. When we observe a supernova, we witness the brilliant final moment of a dying star. For ancient humans, these sudden new lights in the sky were omens, portents of great change. The Chinese, Arabic, and European astronomers who recorded these events had no idea what they were truly seeing. They could not have imagined that they were watching the death throes of distant suns, explosions so powerful they could outshine entire galaxies. But the true transformation, the one that matters most, happens in the silence afterward. Today, we are traveling to the core of one of these collapsing giants. We will observe the exact instant of its demise and see how, from the remnants, a black hole emerges. We are going to approach the boundary of space-time itself and look into the void. This is more than a story of endings. It is also a story about how the universe creates its most powerful and enigmatic objects. The journey begins not with death, but with birth. To understand how a star dies, we first need to appreciate how it lives. Our sun is relatively modest, a small and peaceful star that will burn steadily for around 10 billion years. It formed about 4.5 billion years ago from a cloud of gas and dust, and it has spent all that time in a state of comfortable stability. When it finally runs out of fuel, billions of years from now, it will swell into a red giant and then quietly shed its outer layers, leaving behind a dense ember called a white dwarf. There will be no explosion, no black hole, just a slow, gentle fading. Our sun is what astronomers classify as a G-type main sequence star, sometimes called a yellow dwarf, though calling it yellow is somewhat misleading, since it actually appears white when viewed from space. It sits comfortably in the middle range of stellar masses and temperatures. Stars come in an extraordinary variety of sizes, masses, temperatures, and colors. The smallest stars, so-called red dwarfs, can be as little as 8% the mass of the Sun. These tiny stars burn their fuel so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe. Proxima Centauri, the closest star to our solar system other than the Sun, is a red dwarf located about 4.2 light-years away. This small star has a mass of only about 12% that of our Sun, and it will continue burning for several trillion more years. In fact, every red dwarf that has ever formed, going all the way back to the earliest generation of stars, is still alive today. Not one has reached the end of its natural lifespan. The universe simply has not existed long enough for even the oldest red dwarfs to die. On the other end of the spectrum are the blue hypergiants, monsters that can exceed 200 times the mass of our Sun and burn millions of times brighter. These stars are so luminous that they can be seen from millions of light-years away, yet they are exceedingly rare. The most massive star currently known is R13601, located in the Large Magellanic Cloud, with an estimated mass of about 260 times that of our Sun. Such massive stars are constantly shedding material through powerful stellar winds, and their lifetimes are measured in mere millions of years. But we are interested in the true giants of the cosmos, stars that weigh anywhere from 8 to more than 100 times what our Sun weighs. These massive stars form in the densest regions of giant molecular clouds, where gravity can gather enough material to create something truly enormous. Giant molecular clouds are vast regions of space filled with hydrogen, gas, and dust, stretching for hundreds of light-years and containing enough material to form tens of thousands or even millions of stars. Within these clouds, the densest regions begin to collapse under their own gravity, fragmenting into smaller clumps that will each become individual stars or star systems. The process of star formation within these clouds is remarkably complex. As a region begins to collapse, it heats up due to the conversion of gravitational potential energy into thermal energy. At the same time, the collapsing gas must radiate away this heat energy, or the thermal pressure will halt the collapse before a star can form. This delicate balance between heating and cooling determines which stars can form and how massive they become. In regions where cooling is efficient, the gas can fragment into many smaller clumps, forming clusters of lower mass stars. In regions where cooling is less efficient, or where the gas density is extremely high, larger clumps can survive without fragmenting, potentially forming massive stars. The Orion Nebula, located about 1,300 light-years from Earth, is one of the closest regions of active star formation and provides an excellent laboratory for studying these processes. Within the nebula, we can observe stars at various stages of formation, from dense cores just beginning to collapse to young stars that have already ignited nuclear fusion. The brightest stars in the trapezium cluster at the heart of the Orion Nebula are massive stars that have already formed, and their intense radiation is now affecting the formation of new stars in the surrounding cloud. From the instant these massive stars ignite, their destiny is already determined. All that enormous mass means they burn fiercely, live violently, and die young. A star 100 times the mass of the Sun might live for only 3 million years. In cosmic terms, that is barely an instant. To put this in perspective, humans have existed for only a few 100,000 years. Recorded human history spans only about 5,000 years. A massive star's entire lifetime, from birth to death, could pass in less time than humans have existed on Earth. Meanwhile, a red dwarf with 1/10 the mass of the Sun could burn for 10 trillion years. The universe itself is only about 14 billion years old, meaning no red dwarf has ever died of old age. Not a single one. Every red dwarf that has ever formed is still shining today. Picture a massive star not as a simple sphere of flame, but as a vast, layered structure, like a cosmic onion. At its center lies the core, the power source of the star. Here, conditions are extreme beyond anything found on Earth. Temperatures climb into the millions of degrees, and pressures are intense enough to crush solid mountains into individual atoms. This is where the crucial reactions occur. A star generates its light by fusing elements together deep in its core, releasing enormous amounts of energy in the process. To understand this process, imagine trying to push two magnets together with the same poles facing each other. They resist, they push apart. Atomic nuclei behave similarly because they all carry positive electric charges, and like charges repel. This electromagnetic force is one of the four fundamental forces of nature, and it is incredibly powerful at small scales. In the everyday world, this electromagnetic repulsion keeps atoms separate. It is why you cannot push your hand through a table, why solid objects feel solid, why matter takes up space. The electrons in the atoms of your hand repel the electrons in the atoms of the table, creating an impenetrable barrier at the quantum level. The electromagnetic force operates according to principles discovered in the 19th century by physicists like Michael Faraday and James Clerk Maxwell. Maxwell's equations, a set of four elegant mathematical relationships, describe how electric and magnetic fields interact and propagate through space. These same equations explain everything from how radio waves travel, to how your cell phone works, to why nuclei resist fusion. The electromagnetic force acts over infinite distances, though its strength decreases with the square of the distance. This means if you double the distance between two charged particles, the force between them decreases by a factor of 4. But in the core of a star, temperatures are so high and particles move so fast that when nuclei collide, they overcome this repulsion. They get close enough for the strong nuclear force, which operates only at incredibly short distances, to grab hold and bind them together. The strong nuclear force is the most powerful force in nature, but it only operates at distances comparable to the size of an atomic nucleus, roughly 1/10 trillionth of a centimeter. Once nuclei get that close, the strong force overwhelms the electromagnetic repulsion and binds them together. When this happens, a tiny amount of mass converts directly into energy, according to Einstein's famous equation. This is fusion, and it is the most powerful energy source in the universe. Einstein's equation, energy equals mass times the speed of light squared, tells us that even a tiny amount of mass contains an enormous amount of energy. The speed of light is a huge number, roughly 300,000 kilometers per second, and squaring it makes it even larger. This means that converting just 1 kilogram of matter entirely into energy would release roughly 90 trillion joules, equivalent to the energy of about 21 million tons of TNT. The atomic bombs dropped on Hiroshima and Nagasaki in 1945 released energies equivalent to about 15 and 21,000 tons of TNT, respectively. A single kilogram of matter converted to energy would release 1,000 times more energy than those weapons. Stars perform this conversion continuously, turning mass into energy through nuclear fusion. It begins with hydrogen, the simplest and most abundant element in the universe. Hydrogen accounts for about 75% of all normal matter in the universe by mass, and about 92% by number of atoms. It is the first element that formed after the Big Bang, created in the first few minutes of the universe's existence, when conditions were just right for protons and electrons to come together. every other element formed later, either in the cores of stars or in explosive events like supernovae. The star's gravity constantly tries to compress it inward, but the outward force created by nuclear fusion pushes back with equal strength. For millions of years, these two opposing forces, gravity pulling inward and fusion pushing outward, remain locked in a delicate but violent balance. This equilibrium is called hydrostatic equilibrium, and it is what keeps a star stable and shining. The concept of hydrostatic equilibrium is fundamental to understanding stellar structure. At every point inside a star, the inward gravitational force must be exactly balanced by the outward pressure force. If gravity were slightly stronger, the star would contract. If pressure were slightly stronger, the star would expand. This balance is maintained automatically through a kind of stellar thermostat. If the core contracts slightly, it heats up, which increases the fusion rate, which increases the pressure, which pushes the core back out. If the core expands slightly, it cools down, which decreases the fusion rate, which decreases the pressure, which allows the core to contract again. This self-regulating mechanism keeps stars stable for most of their lives. This negative feedback loop is what gives stars their remarkable stability. Consider what would happen without it. If the fusion rate increased without any compensating mechanism, the core would heat up uncontrollably, causing a runaway explosion. If the fusion rate decreased without compensation, the core would collapse immediately. But the thermostat effect ensures that stars remain stable. This stability is why we can predict stellar evolution with such accuracy, modeling the lives of stars from birth to death using computers and the laws of physics. Deep in the core, hydrogen nuclei combine to form helium, producing the light and warmth we observe. The fusion of hydrogen into helium does not happen in a single step. In stars like the Sun, it proceeds through a series of reactions called the proton-proton chain. First, two protons collide with enough energy to overcome their electromagnetic repulsion. One of them transforms into a neutron through a process called beta plus decay, emitting a positron and a neutrino. This creates a nucleus of deuterium, also called heavy hydrogen, which contains one proton and one neutron. The deuterium nucleus then captures another proton to form helium-3, which has two protons and one neutron. Finally, two helium-3 nuclei collide to form helium-4, releasing two protons in the process. The net result is that 4 protons are converted into one helium nucleus, 2 positrons, 2 neutrinos, and a substantial amount of energy in the form of gamma-ray photons. In more massive stars, a different set of reactions, called the carbon-nitrogen-oxygen cycle, or CNO cycle, dominates hydrogen fusion. In this cycle, carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the conversion of hydrogen to helium. The carbon nucleus captures a proton to become nitrogen, which then captures another proton to become oxygen, and so on through a series of reactions that eventually return the carbon nucleus and produce a helium nucleus. The CNO cycle requires higher temperatures than the proton-proton chain, typically above 15 million degrees, so it dominates in more massive stars where core temperatures are higher. The CNO cycle is more temperature sensitive than the proton-proton chain, meaning the fusion rate increases much more rapidly with temperature. This makes massive stars inherently less stable and more prone to variations in luminosity. Every second, in a star like our Sun, about 600 million tons of hydrogen transforms into helium. The difference in mass between the hydrogen that went in and the helium that comes out, roughly 4 million tons per second, becomes pure energy. This is what makes the Sun shine. To put this in perspective, the Sun converts about 4 million tons of matter into energy every second, and it has been doing this continuously for 4.5 billion years. Even at this rate, the Sun has converted only about 1/20th of 1% of its total mass into energy. It still has enough hydrogen fuel to continue shining for another 5 billion years. In a massive star, this process happens far more rapidly, with fusion rates that dwarf what occurs in our modest Sun. A star 50 times the mass of the Sun might fuse hydrogen at a rate millions of times faster than the Sun, burning through its fuel in just a few million years. Eventually, though, the hydrogen supply runs low and the outward pressure begins to weaken. Gravity, always present and unyielding, starts to take control. It compresses the core even further, driving the temperature and density higher. These new, more extreme conditions are precisely what is needed to ignite the helium that has accumulated. The star now begins fusing helium into carbon. This helium fusion requires temperatures around 100 million degrees, far hotter than hydrogen burning. The helium nuclei are more massive and carry more positive charge, so they resist fusion more stubbornly. Each helium nucleus contains 2 protons, compared to hydrogen's single proton, which means the electromagnetic repulsion between 2 helium nuclei is 4 times stronger than between 2 hydrogen nuclei. Overcoming this requires much higher temperatures and much more violent collisions. But the compressed core of a massive star reaches these extreme temperatures with ease. 3 helium nuclei combine in a delicate process to create 1 carbon nucleus, releasing energy and keeping the star alive for a while longer. The process by which 3 helium nuclei combine to form carbon is called the triple alpha process, named because helium nuclei are also called alpha particles. This reaction is remarkably sensitive to the exact properties of the carbon nucleus. And it turns out that the universe is fine-tuned to allow it to happen efficiently. If the energy levels of the carbon nucleus were slightly different, just a fraction of a percent off from their actual values, the triple alpha process would be far less efficient or would not work at all. This would mean that stars could not produce carbon in significant quantities, and without carbon, the chemistry necessary for life as we know it could not exist. This apparent fine-tuning of the universe's physical constants is one of the deep mysteries of cosmology, and scientists continue to debate its implications. The British astronomer Fred Hoyle predicted the existence of a specific excited state of the carbon nucleus in 1954, reasoning that if carbon were as abundant as observations suggested, there must be a resonance that enhances the triple alpha process. His prediction was confirmed experimentally, and this carbon resonance is now known as the Hoyle state. Hoyle himself saw this as evidence of fine-tuning in the universe. Though whether this fine-tuning implies design or is simply a consequence of the anthropic principle, the idea that we observe these particular physical constants because they are the ones that allow observers to exist remains a topic of philosophical debate. During this stage, the star often swells dramatically in size, becoming what astronomers call a red supergiant. Its outer layers cool and glow with a reddish hue, but deep inside, the core burns hotter than ever. Red supergiants can be truly enormous. Betelgeuse, the bright red star marking the shoulder of the constellation Orion, is a red supergiant roughly 700 to 900 times the diameter of our Sun. If you placed Betelgeuse where our Sun is, its outer surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its expanded envelope. The star UY Scuti, one of the largest known stars, is estimated to have a radius roughly 1,700 times that of the Sun. If placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. These stars are so large that despite containing dozens of times more mass than the Sun, their outer layers are incredibly diffuse, with densities lower than Earth's atmosphere at sea level. The expansion of a star into a red supergiant phase is driven by changes in its internal structure. As the core contracts and heats up to begin helium burning, the increased luminosity from the core drives the outer layers outward. The star's radius can increase by factors of hundreds or even thousands while its surface temperature drops. This expansion is not explosive, but occurs relatively gradually over thousands of years. The outer envelope of the star becomes cool enough that molecules can form and dust grains can condense. These cool supergiants often show evidence of substantial mass loss, with stellar winds carrying away material at rates that can reach 1/1,000,000th of a solar mass per year. Over the star's lifetime, these winds can remove a significant fraction of the star's mass, which affects its ultimate fate. The mass loss from red supergiants is visible as circumstellar shells and nebulae surrounding the stars. VY Canis Majoris, another red supergiant, is surrounded by a complex nebula of ejected material extending for several light years. This material contains molecules and dust grains that condensed in the cool outer atmosphere of the star. When the star eventually explodes as a supernova, the shock wave will collide with this previously ejected material, creating a bright, expanding shell. This interaction between the supernova ejector and circumstellar material produces some of the most spectacular supernova remnants we observe. When the helium is exhausted, the pattern continues. The core contracts again, temperatures rise dramatically, and carbon fuses into heavier elements such as neon, oxygen, and silicon. Each stage creates a new layer, much like the rings of an onion. In the outer regions, hydrogen continues to burn. Beneath that, a shell of helium fuses into carbon, and deeper still, heavier elements are being forged. While a star like our Sun stops after producing carbon and oxygen, a massive star has enough gravitational pressure to continue the process. By the time the star is nearing the end of its life, its internal structure resembles a nested set of shells, each burning a different element. The outermost shell still fuses hydrogen into helium. Moving inward, the next shell burns helium into carbon. Deeper still, carbon fuses into neon and magnesium. Then comes oxygen burning, producing silicon and sulfur. And at the very center, silicon fuses into iron. Each shell is hotter and denser than the one above it, with the iron core at the center reaching temperatures of several billion degrees. The temperatures required for each stage increase dramatically. Hydrogen fusion requires about 10 million degrees. Helium fusion needs 100 million degrees. Carbon burning requires around 600 million degrees. Neon burning happens at about 1 billion degrees. Oxygen burning needs roughly 2 billion degrees. And silicon burning, the final stage, occurs at temperatures exceeding 3 billion degrees. Each stage requires progressively higher temperatures because heavier nuclei carry more positive charge and resist fusion more strongly. Silicon has 14 protons, and overcoming the electromagnetic repulsion between two silicon nuclei requires an enormous amount of energy. This mechanism, called stellar nucleosynthesis, is how the universe manufactures heavy elements. Every atom heavier than helium in your body was created inside a star. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, the silicon in Earth's crust, all of it was created inside stars that perished long before our solar system formed. When those ancient stars exploded, they scattered these elements into space, enriching the clouds of gas and dust that would eventually collapse to form new stars, planets, and ultimately, life itself. We are, quite literally, made of stardust. The concept that we are made of stardust is not just poetic language. It is literal scientific fact. When the solar system formed 4.5 billion years ago, it condensed from a cloud of gas and dust that had been enriched by countless previous generations of stars. That cloud contained hydrogen and helium from the Big Bang, but it also contained carbon, nitrogen, oxygen, silicon, iron, and all the other heavy elements created by stars that lived and died before our sun was born. Every atom of carbon in the DNA that encodes your genetic information, every atom of oxygen in the water molecules that make up most of your body, every atom of nitrogen in the proteins that form your muscles, every atom of calcium that gives your bones their strength, every atom of iron in the hemoglobin that carries oxygen in your blood. All of these atoms were forged in the nuclear furnaces of ancient stars and scattered into space when those stars died. In a very real sense, you are a collection of stardust, organized by 4 billion years of evolution into a pattern complex enough to contemplate its own origins. Consider the journey of a single carbon atom in your body. It was created perhaps 8 billion years ago, in the core of a red giant star that fused 3 helium nuclei together. When that star died, either in a supernova or by gently puffing off its outer layers, the carbon atom was released into the interstellar medium. For billions of years, it drifted through space, perhaps becoming part of a new gas cloud, perhaps being incorporated into a new star and then released again. Eventually, about 4.5 billion years ago, it became part of the solar nebula, the cloud that collapsed to form our solar system. It might have spent time in various locations, perhaps in asteroids or comets, before eventually becoming part of Earth. On Earth, it cycled through rocks, the atmosphere, and living organisms. At some point, it was incorporated into a plant through photosynthesis, then consumed by an animal, passed through various food chains, and eventually became part of you. And after you die, it will continue its journey, returning to the environment and eventually, billions of years from now, perhaps leaving Earth entirely and becoming part of a new star system. Every atom has a story, and that story spans the entire history of the cosmos. But this accelerating cycle cannot continue indefinitely. Each stage of fusion happens faster than the one before. Hydrogen burning lasts millions of years. Helium burning takes only a few 100,000 years. Carbon fusion might continue for several centuries. Oxygen burning lasts perhaps a year. The final stage, silicon fusion, could be over in just one day. The star is running out of time. With each stage, the energy released per fusion reaction decreases, while the energy required to ignite the next stage increases. The star is climbing an ever steeper hill, and it is running out of strength. The reason for this dramatic acceleration is rooted in basic physics. Each heavier element contains more protons in its nucleus, which means more electromagnetic repulsion to overcome. This requires higher temperatures to initiate fusion. Higher temperatures mean the star's core must contract more, which happens faster as the core grows denser. At the same time, each stage produces less energy per fusion reaction. Fusing hydrogen into helium releases about 7 million electron volts of energy per helium nucleus produced. Fusing helium into carbon releases less energy per nucleus. Fusing carbon, oxygen, and silicon release progressively less energy. The star is working harder and harder to sustain itself while getting less and less return on its effort. It is like running faster and faster on a treadmill that keeps increasing in speed, knowing that eventually you will not be able to keep up. Eventually, the star produces iron, and iron changes everything. Unlike every element before it, fusing iron does not produce energy. Instead, it absorbs energy. This is because iron sits at the peak of what physicists call the nuclear binding energy curve. This curve describes how tightly bound atomic nuclei are, or equivalently, how much energy you would need to completely disassemble a nucleus into individual protons and neutrons. Elements lighter than iron release energy when fused together. Elements heavier than iron release energy when split apart, but iron itself is perfectly balanced. It is the most stable nucleus in nature, the bottom of the energy hill. Fusing it requires an input of energy rather than producing an output. The core, which has been the star's engine for its entire existence, becomes a drain on the system. Understanding why iron is special requires understanding the nuclear forces at work inside atomic nuclei. The strong nuclear force binds protons and neutrons together, but it only operates at very short ranges. Protons also repel each other through the electromagnetic force, and this repulsion acts over longer ranges. In light nuclei, the attractive strong force outweighs the electromagnetic repulsion because the nucleus is small and all the particles are close together. As nuclei get heavier and larger, the electromagnetic repulsion grows stronger because there are more protons pushing against each other. Iron and nickel sit at the sweet spot where the attractive strong force and the repulsive electromagnetic force balance most efficiently. Going beyond iron means adding more protons, which increases electromagnetic repulsion faster than it increases strong force attraction, making heavier nuclei less stable than iron. This is why iron represents the end point of stellar fusion. The star can go no further. It is worth noting that iron is not exactly the most stable nucleus. That distinction belongs to nickel-58, which has a slightly higher binding energy per nucleon than iron-56. However, the nuclear reactions in stellar cores primarily produce iron-56 rather than nickel-58 for reasons related to the specific reaction pathways available at stellar temperatures. The difference in stability is small enough that iron is commonly referred to as the peak of the binding energy curve. In any case, both iron and nickel represent the practical endpoint of energy-generating fusion in stars. Beyond this point, no energy can be extracted by combining nuclei. The iron core at the center of the dying star grows steadily as silicon burning continues in the shell above it. Within about a day, the core contains more than 1.5 times the mass of the Sun, compressed into a sphere about the size of Earth. The core is composed primarily of iron-56 nuclei, with smaller amounts of other iron group elements like cobalt, nickel, and chromium. The temperature is about 5 billion degrees, and the density approaches that of an atomic nucleus. Despite these extreme conditions, the core is not producing energy. It is merely sitting there, supported by electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs. But this support is temporary. The iron core is growing, and it is approaching the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support. Imagine a fire that has burned for millions of years suddenly being doused with water. The nuclear furnace at the heart of the star shuts down. In an instant, the outward pressure that has resisted gravity for millions of years disappears. The balance is broken. Gravity wins. And when gravity wins in a massive star, the consequences are catastrophic. What follows is among the fastest and most catastrophic events in the cosmos. With the furnace extinguished, there is nothing left to support the star's immense outer layers. Gravity takes complete control. The iron core, roughly the size of Earth but containing more than 1.5 times the mass of our Sun, begins to collapse inward. The word collapse does not do it justice. This is an implosion of staggering speed. The outer layers of the star fall inward at velocities approaching 1/4 the speed of light. That is roughly 75,000 kilometers per second. To put that in perspective, at that speed, you could travel from Earth to the Moon in less than 5 seconds. You could circle Earth's equator more than twice in 1 second. If you could somehow board a spacecraft traveling at this speed, you could reach the Sun 150 million kilometers away in about half an hour. A mass the size of a planet is crushed down to the size of a city in less than 1 second. The black hole, or the object that will become one, can form in just fractions of a second. In the span of time it takes for a single heartbeat, an object containing more mass than our Sun is compressed from the size of Earth to the size of a small city. The speed of this collapse is determined by freefall under gravity, and the numbers are staggering. When the core's internal pressure disappears, every layer of the star suddenly finds itself in freefall, accelerating inward under the pull of gravity. The acceleration is enormous because there is so much mass concentrated in such a small volume. The gravitational acceleration at the surface of the collapsing core can exceed 100 billion times Earth's surface gravity. If you could somehow stand on the surface of this collapsing core, which you cannot because you would be instantly vaporized, you would experience a force pulling you downward with a strength 100 billion times greater than what you feel standing on Earth. Your weight would increase by a factor of 100 billion. No material in the universe could withstand such forces. As the core implodes, temperatures and densities reach almost unimaginable levels. The temperature climbs beyond 100 billion degrees, more than 6,000 times hotter than the center of the Sun. The density becomes so extreme that a single cubic centimeter of this material would weigh as much as a mountain. In this extreme environment, high-energy photons tear apart iron nuclei in a process known as photodisintegration, reversing the fusion reactions that took the star millions of years to complete. Think of it this way. The star spent its entire life building up heavy elements from lighter ones, climbing up the periodic table one fusion reaction at a time. It started with hydrogen and patiently fused it into helium over millions of years. Then it fused helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron, each step requiring more energy and happening faster than the last. Now, in the final moments, all that work is being undone. Iron nuclei are being ripped back apart into helium and individual protons and neutrons. This drains even more energy from the system, accelerating the collapse further. It is like removing the final support column from a building that is already falling. The collapse feeds on itself, becoming faster and more violent with each passing millisecond. Photodisintegration requires enormous amounts of energy. To tear apart an iron nucleus into its constituent protons and neutrons requires millions of electron volts per nucleus. But at temperatures exceeding 100 billion degrees, there is more than enough energy available. The gamma-ray photons racing through the collapsing core carry millions or tens of millions of electron volts each, far more than enough to blast iron nuclei apart. This process absorbs energy that would otherwise contribute to the pressure supporting the core, so photodisintegration accelerates the collapse by removing yet another source of support. It is catastrophic positive feedback. The core collapses, which increases the temperature, which causes more photodisintegration, which removes more pressure support, which causes more collapse, and the cycle repeats, faster and faster. At the same time, the intense pressure forces electrons and protons together, creating vast numbers of neutrons and releasing ghostly particles called neutrinos. Neutrinos are among the strangest particles in physics. They have almost no mass, no electric charge, and interact so weakly with matter that they can pass through solid lead as easily as light passes through glass. Neutrinos rarely interact with ordinary matter. Trillions of them from the sun pass through your body every second without effect. Most of them pass through the entire Earth without interacting with a single atom. You could stack lead blocks 1 light year thick, and a typical neutrino would still have better than even odds of passing through without interacting. Neutrinos come in 3 types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They can oscillate between these flavors as they travel through space, a quantum mechanical phenomenon that was only confirmed experimentally in the late 1990s. This discovery revealed that neutrinos must have mass, though their masses are extremely small, millions of times lighter than electrons. The exact masses of neutrinos remain one of the open questions in particle physics, but we know they are not massless as was once thought. The process that creates neutrons and neutrinos is called neutronization or electron capture. Under normal circumstances, electrons and protons remain separate particles. They are attracted to each other electromagnetically, which is why electrons orbit atomic nuclei, but they remain distinct. However, at the extreme densities and pressures inside the collapsing core, electrons are forced so close to protons that they can merge through the weak nuclear force, one of the 4 fundamental forces of nature. When an electron and proton merge, they form a neutron and emit an electron neutrino. This process transforms the iron core, which was made of iron nuclei surrounded by free electrons, into a sea of pure neutrons. But inside this collapsing core, where densities are extreme, they play a critical role. In the first second of core collapse, the star produces more neutrinos than the sun will produce in its entire 10 billion year lifetime. So many neutrinos are generated that they carry away tremendous amounts of energy, preventing the core from heating up enough to resist the collapse. In that first second, the star releases more energy in neutrinos than all the stars in the observable universe are emitting in light at that same moment. This neutrino cooling is the final step, ensuring that the collapse is rapid and complete. The energy carried away by neutrinos is almost unimaginable. In the first second of collapse, the core releases roughly 10 to the power of 46 joules of energy, which is about 100 times more energy than the sun will emit in light over its entire 10 billion year lifespan. Almost all of this energy, about 99%, is carried away by neutrinos. Only about 1% is released in the form of light and kinetic energy of the exploding star. This means that if you could somehow detect neutrinos as easily as you detect light, a nearby supernova would appear 100 times brighter in neutrinos than it does in light. The neutrino burst from a supernova is so intense that a supernova occurring 10 light years from Earth would deliver enough neutrino energy to every square centimetre of your body to be lethal. Even though neutrinos normally interact so weakly with matter that they are essentially harmless, the detection of neutrinos from supernovae represents one of the great triumphs of experimental physics. In 1987, a supernova exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, located about 160,000 light-years from Earth. This supernova, designated SN 1987A, was the closest supernova visible to the naked eye since Kepler's supernova in 1604. Several neutrino detectors around the world, including the Kamiokande detector in Japan and the IMB detector in the United States, detected a burst of about 24 neutrinos arriving from the direction of the supernova. These detections occurred several hours before the light from the supernova reached Earth, confirming theoretical predictions that neutrinos escape from the core before the shockwave reaches the surface. Out of the roughly 10 to the power of 58 neutrinos emitted by the supernova, only about 20 were detected on Earth, illustrating just how weakly neutrinos interact with matter. Yet this handful of detections provided crucial confirmation of our understanding of core collapse supernovae. The neutrino signal from SN 1987A arrived at Earth over a period of about 13 seconds. The fact that neutrinos arriving over this time span all came from the same event and that they arrived a few hours before the visible light told astronomers several important things. First, it confirmed that the neutrinos were produced in the core collapse itself, not later in the explosion. Second, the time spread of 13 seconds gave information about the cooling time of the newborn neutron star. Third, the fact that all the neutrinos arrived within a short time window despite traveling 160,000 light-years placed tight constraints on the neutrino mass. If neutrinos had significant mass, they would travel at speeds below the speed of light, and neutrinos of different energies would arrive at different times, spreading out the signal. The observation that they all arrived within 13 seconds implies that neutrino masses are very small. The core continues to compress until it transforms into a dense, rigid sphere made entirely of neutrons, packed together as tightly as the laws of physics allow. This neutron matter is so dense that a single teaspoon would weigh more than every mountain on Earth combined. A sugar cube of neutron star material would weigh as much as all of humanity. This neutron core cannot be compressed any further. The neutrons themselves resist being pushed closer together through a quantum mechanical effect called degeneracy pressure. They have reached a state where the core is essentially one giant atomic nucleus, held up not by fusion or thermal pressure, but by the quantum resistance of neutrons being forced into the same space. Degeneracy pressure is a purely quantum mechanical phenomenon with no analogue in everyday experience. It arises from the Pauli exclusion principle, one of the fundamental laws of quantum mechanics, which states that no two identical fermions can occupy the same quantum state simultaneously. Neutrons are fermions, which means they obey this rule. When neutrons are packed together at extremely high densities, they are forced into higher and higher energy states because the lower energy states are already occupied. This creates an outward pressure that resists further compression. This degeneracy pressure depends only on density, not on temperature, which makes it fundamentally different from the thermal pressure that supports ordinary matter. In a neutron star, degeneracy pressure is strong enough to support roughly 1.5 to 3 times the mass of the Sun in a sphere only about 20 kilometers across. The interior of a neutron star is structured in layers, much like Earth's interior. At the surface, there is a thin crust, perhaps a kilometer thick, composed of atomic nuclei in a crystalline lattice, similar to a metal but far denser. Below the crust, the density increases and nuclei become more neutron-rich, with neutrons beginning to drip out of nuclei and move freely. Deeper still, in the outer core, the matter is primarily a superfluid of neutrons, with a small fraction of protons and electrons. The neutrons form Cooper pairs and flow without friction, a quantum phenomenon with no resistance. In the inner core, the density may be so high that exotic forms of matter appear, such as hyperons, strange matter, or even quark matter, where neutrons break down into their constituent quarks. The exact state of matter in the inner core remains uncertain because we cannot reproduce these densities in laboratories. The rest of the star, still plummeting inward at a significant fraction of the speed of light, crashes into this immovable wall of neutrons and rebounds. Imagine dropping a rubber ball onto concrete. The ball compresses slightly when it hits, then springs back and bounces. Something similar happens here, except the ball is the mass of the Sun and it is falling at 1/4 the speed of light. The rebound is violent beyond comprehension. When the infalling material hits the surface of the neutron core, it does not simply stop. It crashes into the rigid neutron surface and bounces back like a wave hitting a breakwater. This creates a shock wave, a moving wall of compressed, superheated material that begins traveling back outward through the star. This rebound generates an enormous shockwave that begins traveling back outward through the star. For many years, scientists believed this shockwave alone was responsible for the explosion. The idea was simple. The bounce would create a shockwave powerful enough to blast through the star's outer layers and blow them into space. It seemed logical. The infalling material carries an enormous amount of kinetic energy, and when it slams into the rigid neutron core, all that energy has to go somewhere. Surely it would be enough to reverse the infall and blow the star apart. However, modern three-dimensional computer simulations reveal that the shockwave loses momentum, unable to overcome the torrent of infalling material. Within milliseconds, the shockwave stalls, trapped between the infalling outer layers and the newborn neutron core. As the shockwave tries to push outward, it runs into layer after layer of material still falling inward at tremendous speeds. The collision between the outward moving shockwave and the inward falling material robs the shockwave of energy. Additionally, as the shockwave moves through the iron-rich layers near the core, it triggers photodisintegration, breaking apart iron nuclei and absorbing even more energy. Within a few milliseconds, the shockwave stalls at a radius of a few hundred kilometers, unable to make further progress. The star seems poised on the edge between explosion and further collapse. It requires additional energy. Understanding why the prompt explosion mechanism fails required decades of increasingly sophisticated computer simulations. Early one-dimensional models, which assumed perfect spherical symmetry, suggested the prompt mechanism might work, but the universe is not perfectly symmetric. Two-dimensional and three-dimensional simulations revealed that convection, turbulence, and asymmetries play crucial roles in the explosion mechanism. The stalled shockwave is not stable. It develops large-scale convective overturn, with hot bubbles of material rising and cool streams of material falling. These convective motions increase the efficiency of neutrino heating, helping to revive the shock. That energy comes from the neutrinos still streaming out of the core. Remember those ghostly particles that rarely interact with anything? In the dense material behind the stalled shockwave, conditions are so extreme that even neutrinos start interacting with matter. The density behind the stalled shockwave is so high that the neutrinos streaming out of the core have a small but non-negligible chance of colliding with nuclei and transferring their energy. A small fraction, perhaps 1%, of these neutrinos collide with matter, reheating it and injecting it with tremendous force. It might not sound like much, but when you are dealing with numbers this large, 1% of an unimaginable amount is still an unimaginable amount. This neutrino-driven energy boost gives the shockwave the power it needs to succeed. Over the course of seconds, the shockwave gathers strength. The neutrinos deposit enough energy to heat the material behind the shock to billions of degrees, creating tremendous pressure. This reheated material begins to expand, driving the shockwave outward. Convective motions develop behind the shock, with hot material rising and cool material sinking, stirring the region and helping to absorb more neutrino energy. After what might be a few tenths of a second or several seconds, depending on the details of the star's structure and the physics involved, the shockwave gains enough energy to overcome the infalling material and begin moving outward in earnest. The revitalized shockwave tears through the star's outer layers, igniting one final burst of explosive fusion and creating even more heavy elements. As the shockwave rips through these outer layers, it compresses and heats the material, triggering fusion reactions that would never occur under normal circumstances. This is where many of the heaviest elements in the universe are made, elements like gold, platinum, and uranium. These elements require so much energy to create that they can only be forged in the violence of a supernova explosion. Gold, for example, requires the fusion of many lighter nuclei, or the rapid capture of many neutrons by lighter nuclei, both processes that require enormous amounts of energy. The R process, or rapid neutron capture process, is thought to be the primary mechanism for creating elements heavier than iron. In the incredibly neutron-rich environment behind the supernova shockwave, atomic nuclei are bombarded with neutrons and rapidly build up to heavier and heavier elements. This process happens so quickly that unstable isotopes do not have time to decay before capturing more neutrons, allowing the buildup of very heavy elements. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear power plants, all of it was created in supernova explosions or in collisions between neutron stars scattered into space and eventually incorporated into our planet. Recent research has revealed that neutron star mergers may be even more important than supernovae for producing the heaviest elements. When two neutron stars spiral together and collide, they create an environment even more neutron-rich than a supernova, making them ideal factories for our process elements. In 2017, the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars, an event designated GW170817. This merger was also observed by telescopes across the electromagnetic spectrum, making it the most thoroughly studied astronomical event in history. Observations of the light from the merger revealed the spectral signatures of newly synthesized heavy elements, confirming that neutron star mergers are major sources of gold, platinum, and other precious metals. The amount of gold produced in this single merger was estimated to be several times the mass of Earth. The light emitted from neutron star mergers has a distinctive red color due to the opacity of the heavy elements produced. This type of transient event is called a kilonova. The peak brightness occurs about a day after the merger, and the light fades over the course of weeks. The color evolution of the kilonova provides information about which elements were produced. Early theoretical predictions of kilonovae suggested they would be bright in ultraviolet and blue light, but observations of GW170817 showed that the kilonova was much redder than expected, indicating the production of very heavy elements with high opacity. This observation has led to refinements in our understanding of R-process nucleosynthesis and the conditions in neutron star merger ejecta. At last, the shockwave reaches the surface of the star, and the universe witnesses a supernova. From our perspective, the star suddenly grows brighter until it rivals the combined light of its entire host galaxy. For several weeks, it blazes with the intensity of 100 billion suns before gradually dimming. If a supernova occurred within a few dozen light years of Earth, it would be bright enough to cast shadows at night and would be visible during the day. The peak brightness of a typical core collapse supernova is around 10 billion times the luminosity of the Sun. At this brightness, a supernova located 10 light-years from Earth would appear as bright as the Sun, even though it is 63,000 times farther away. A supernova 30 light-years away would appear as bright as the full moon. It would completely dominate the night sky, bright enough to read by, and would be visible in broad daylight. Astronomers have calculated that a supernova within about 30 light-years could have significant effects on Earth's atmosphere and climate. The high-energy radiation, particularly X-rays and gamma rays, could partially strip away the ozone layer, increasing the amount of ultraviolet radiation reaching the surface. This could affect plant life and marine phytoplankton, potentially causing disruptions to the food chain. Fortunately, there are no massive stars close enough to pose such a threat. The nearest star capable of going supernova, Spica, is about 250 light-years away, far enough that its eventual explosion will be spectacular but harmless. Ancient astronomers recorded several such events as new stars appearing in the sky. In the year 185, Chinese astronomers recorded what they called a guest star that appeared in the constellation we now call Centaurus. It was visible for 8 months before fading from view. Modern astronomers have identified the remnant of this supernova, known as RCW 86. In the year 1054, Chinese astronomers observed a supernova so bright it was visible in daylight for 23 days. The remnant of that explosion is now known as the Crab Nebula, a beautiful, expanding cloud of gas and dust located about 6,500 light-years from Earth. At its center sits a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. The Crab pulsar rotates about 30 times per second, and each rotation sends a pulse of radiation sweeping across Earth like the beam of a lighthouse. In 1572, the Danish astronomer Tycho Brahe observed a supernova in the constellation Cassiopeia that was bright enough to be visible in daylight. Tycho's careful observations of this new star, which did not move relative to the other stars, helped convince astronomers that the heavens were not unchanging and perfect as Aristotelian philosophy had taught. In 1604, Johannes Kepler observed another supernova in the constellation Ophiuchus, which was also visible in daylight. These supernovae, observed before the invention of the telescope, profoundly influenced our understanding of the cosmos and helped pave the way for the scientific revolution. No supernova visible to the naked eye has been observed in our galaxy since Kepler's supernova, though astronomers estimate that several should have occurred based on the expected supernova rate. The absence of observed supernovae in our galaxy over the past 4 centuries is somewhat puzzling. Based on the rate of massive star formation in the Milky Way, astronomers estimate that a supernova should occur every 50 to 100 years on average. This suggests that 2 to 8 supernovae should have occurred since Kepler's time, yet none have been observed. The most likely explanation is that these supernovae occurred in regions of the galaxy obscured by dust, preventing their light from reaching us. The Milky Way is a dusty galaxy, and much of the galactic plane is hidden from our view by intervening clouds of dust and gas. Supernovae occurring on the far side of the galaxy or in the plane of the galaxy might be completely obscured. Alternatively, we may simply have been unlucky, and the actual supernova rate may be on the lower end of current estimates. The explosion scatters the star's outer layers into space at speeds of tens of thousands of kilometers per second. These expanding shells of gas, enriched with all the elements the star created during its life and death, will eventually mix with the interstellar medium. The expanding supernova remnant can sweep up material as it plows through space, creating a shell of shocked, compressed gas that glows brightly in X-rays and radio waves. Over time, the remnant will fade and disperse, but its effects on the surrounding interstellar medium will persist for millions of years. The shockwave from the supernova can trigger the collapse of nearby gas clouds, initiating new episodes of star formation. The heavy elements ejected by the supernova enrich the interstellar medium, raising the metallicity of future generations of stars and planets. Millions or billions of years later, some of that material will collapse to form new stars and planets, continuing the cosmic cycle of death and rebirth. Our solar system formed from material enriched by countless previous generations of stars. The Sun is considered a third-generation star, meaning it formed from gas that had already been through at least 2 cycles of star formation, stellar evolution, and supernova explosion. The heavy elements in Earth's crust, in our oceans, in our atmosphere, and in our bodies, all came from ancient supernovae. Every breath you take contains oxygen atoms that were forged in the core of a massive star and scattered into space by a supernova explosion billions of years ago. But this is not the only way a massive star can end. If the star is massive enough, the collapse can be so thorough that nothing escapes at all. In these direct collapse scenarios, there is no spectacular explosion. The star simply disappears, falling directly into a black hole as if someone turned off a switch. Astronomers call these failed supernovae or collapses. The physics of why some stars explode and others collapse directly into black holes is still not fully understood, but it appears to depend on the detailed structure of the star and the strength of the neutrino-driven explosion mechanism. From the outside, the star would simply fade from view over the course of days or weeks, dimming as its outer layers followed the core into oblivion. No fireworks, no expanding shell of gas, just a silent exit from the cosmic stage. You might see some light as the outer layers heat up during the initial collapse, but instead of brightening to supernova intensity, the star would dim and vanish. These events are incredibly difficult to detect because they produce very little light. Astronomers have to monitor millions of stars continuously and look for stars that simply disappear. Several candidate failed supernovae have been identified in recent years, including a red supergiant in the galaxy NGC 6812 that brightened slightly and then vanished from view between 2009 and 2015. Other times, a supernova does occur, but the explosion is not powerful enough to eject all of the star's material. Much of it is blown outward initially, only to fall back down, overcome by the enormous gravity of the remnant left behind. This is called fallback, and it means the final black hole ends up more massive than the initial neutron core. Computer simulations show that fallback is probably common in supernova explosions. The explosion might successfully eject the outer layers of the star, but the inner layers, which were closer to the core and experienced less of the neutrino heating, fall back onto the neutron star. Over time, this infalling material adds mass to the neutron star, and if enough material falls back, it can push the neutron star over the mass limit that neutron degeneracy pressure can support. In some extreme cases, the star undergoes a series of pulses, partially exploding and then collapsing again, before finally settling into its final state. These pulsational pair instability supernovae occur in the most massive stars, those exceeding 100 times the mass of the Sun. In these stars, the core becomes so hot that photons spontaneously convert into electron-positron pairs, a process called pair production. This removes energy from the photon radiation field, causing a sudden drop in radiation pressure. The core contracts rapidly, triggering explosive burning that partially disrupts the star. But the core survives and continues to contract, and the process can repeat multiple times before the star finally explodes completely or collapses into a black hole. These exotic events may have been more common in the early universe, when metal-poor stars could grow to enormous sizes. In either situation, whether a failed supernova or a direct collapse, if the object remaining at the center is too massive, more than roughly 3 times the mass of our Sun, no known force can prevent gravity's ultimate triumph. The remnant continues to compress itself beyond all known physical limits until it becomes a black hole. This mass limit, called the Tolman-Oppenheimer-Volkoff limit, represents the absolute maximum mass that neutron degeneracy pressure can support. Beyond this point, not even the quantum resistance of neutrons can hold back gravity. The exact value of this limit depends on the equation of state of neutron star matter, which is still not perfectly known because we cannot recreate these extreme densities in laboratories. Current estimates place the limit somewhere between 2 and 3 solar masses, though recent observations of very massive neutron stars have pushed the limit higher. The supernova dims, the explosion fades. Where a brilliant star once burned, something entirely different now exists in the darkness. Something that distorts the very structure of space-time around it. A black hole has formed. To understand what this means, you need to set aside everyday intuition. A black hole is not a cosmic vacuum cleaner sucking things in. It is a region of space-time where gravity has become so powerful that the velocity needed to escape exceeds the speed of light. Because nothing in the universe can move faster than light, anything that crosses this boundary is trapped forever. Think about escape velocity for a moment. If you throw a ball upward, Earth's gravity pulls it back down. But if you could throw it fast enough, around 11 kilometers per second, it would escape Earth's gravity entirely and never fall back. That speed is Earth's escape velocity. This is why rockets need to accelerate to such high speeds to leave Earth. They must reach at least 11 kilometers per second relative to Earth's surface, accounting for air resistance and gravitational losses, which requires even higher speeds. If you threw a ball upward at 10 kilometers per second, it would rise very high, perhaps hundreds of kilometers, but it would eventually fall back. At 11.2 kilometers per second, it would escape completely. The Moon has a lower escape velocity because it is less massive. You could escape the Moon's gravity by jumping at just 2.4 kilometers per second. Jupiter has a higher escape velocity because it is more massive. Escaping Jupiter's gravity requires a speed of about 60 kilometers per second. White dwarfs, which pack about the mass of the Sun into an object the size of Earth, have escape velocities of a few thousand kilometers per second. Neutron stars, packing about 1.5 solar masses into a sphere only 20 kilometers across, have escape velocities of around half the speed of light. Now imagine an object so massive and so compressed that its escape velocity exceeds 300,000 kilometers per second, the speed of light. That is a black hole. This boundary is not a physical surface you could touch. It is an invisible, one-way threshold known as the event horizon. It represents the point of no return. The event horizon is defined purely by geometry and gravity. At the event horizon, space-time is curved so strongly that any path that starts inside the horizon and moves forward in time must end at the singularity. There is no trajectory, no matter how clever, that allows you to escape. You could fire your rocket engines at full power, you could use every ounce of fuel you have, and it would not matter. You would still fall inward. According to our best models, the event horizon actually forms before the star's matter finishes collapsing into the singularity, the infinitely dense point at the center where our understanding of physics breaks down. The event horizon is defined not by the matter itself, but by the geometry of space-time around it. It is the surface where space-time curves so steeply that all future paths lead inward. Mathematically, the radius of the event horizon, called the Schwarzschild radius, is proportional to the mass of the black hole. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole 3 times the mass of the Sun, the Schwarzschild radius is about 9 kilometers. For a supermassive black hole 1 billion times the mass of the Sun, the Schwarzschild radius is about 3 billion kilometers, roughly the radius of Uranus's orbit. Once you pass through the event horizon, every possible path leads in only one direction, inward. You could fire your rocket engines at maximum thrust, you could accelerate to speeds approaching light itself, and it would make no difference. All roads lead to the singularity. The singularity is no longer a location in space. Instead, it becomes an inevitable moment in your future, as unavoidable as tomorrow. This is one of the most profound and unsettling implications of general relativity. Beyond the event horizon, the concepts of space and time trade roles. What was once a direction in space, the radial direction toward the center, becomes a direction in time, leading inevitably toward the singularity. You cannot avoid moving toward the singularity any more than you can avoid moving forward in time. For an outside observer, watching this formation is a peculiar experience. The extreme gravity stretches light from the collapsing matter toward longer, redder wavelengths. Time itself appears to slow down for the infalling material. This is not an illusion. It is a real effect predicted by Einstein's theory of general relativity, called gravitational time dilation. The closer you get to a massive object, the slower your clock runs relative to an observer far away. This effect is very small in everyday situations. GPS satellites, which orbit about 20,000 kilometers above Earth's surface, experience slightly less gravity than at the surface, so their clocks run about 45 microseconds per day faster than clocks on Earth. This tiny difference must be corrected for, or GPS navigation would quickly become inaccurate. From our viewpoint, the last traces of light from the star would seem to freeze at the event horizon, fade toward red, and then disappear completely. We would never actually witness the black hole's formation. We would simply see the star fade into blackness. To the distant observer, the infalling matter takes an infinite amount of time to cross the event horizon, asymptotically approaching the horizon but never quite reaching it. The light from the infalling matter becomes progressively more red-shifted, the photons losing energy as they climb out of the deepening gravitational well, until the photons become so red-shifted that they are effectively invisible. From the perspective of an observer falling into the black hole, however, the experience is very different. They cross the event horizon in a finite, measurable time. They would not notice anything particularly special about the event horizon itself, except that they can now see light from events that occurred after they started falling, light that can now reach them because it started inside the horizon. Because black holes trap all light, they are invisible to us. They are perhaps the darkest objects imaginable, perfect voids in the fabric of space. We can only detect them by observing the disruption they cause in the surrounding space. Any leftover gas from the supernova, or any unfortunate star that strays too close, gets drawn into a spinning, luminous disk called an accretion disk. Modern simulations show that these disks are not the flat, smooth structures often depicted in older illustrations. Powerful magnetic fields cause the disk to puff up, creating a turbulent, fluffy structure more like a chaotic donut. The physics of these accretion disks is extraordinarily complex, involving turbulent fluid dynamics, magnetic field interactions, and relativistic effects. Scientists use supercomputers to simulate these processes, and the results have revealed structures far more intricate and dynamic than anyone imagined decades ago. The disk is threaded with magnetic field lines that get stretched and twisted by the differential rotation. These magnetic fields can become unstable, creating turbulence that transports angular momentum outward, allowing material to spiral inward toward the black hole. As matter spirals inward, friction heats the disk to temperatures of millions of degrees, causing it to emit brilliant X-rays. The material in the inner regions of the disk is moving at a substantial fraction of the speed of light, orbiting the black hole thousands of times per second. At the innermost stable circular orbit, the last place where matter can orbit stably before plunging into the black hole, material is moving at significant fractions of the speed of light and experiencing intense gravitational forces. The friction between adjacent layers of gas converts gravitational potential energy into heat, and that heat radiates away as intense, high-energy radiation. This creates a paradox. The regions surrounding black holes are among the brightest sources of radiation in the universe. The black hole itself is invisible, but the matter swirling around it creates a blazing beacon that can outshine entire galaxies. The accretion disk radiates most intensely in X-rays, a form of light invisible to human eyes but easily detected by X-ray telescopes in space. X-ray astronomy, which began in the 1960s with brief rocket flights carrying X-ray detectors above Earth's atmosphere, has revolutionized our understanding of black holes. Many stellar mass black holes were first discovered as intense X-ray sources, systems where a normal star orbits an invisible companion and loses matter to it. The matter stripped from the star falls toward the black hole, forming an accretion disk that heats up and emits X-rays. By studying the X-ray emission and the motion of the visible star, astronomers can infer the mass of the invisible companion and determine whether it is a neutron star or a black hole. Cygnus X1, discovered in 1964, was one of the first black hole candidates identified. It consists of a blue supergiant star orbiting an invisible companion every 5.6 days. The mass of the invisible companion is estimated to be about 15 times the mass of the Sun, well above the maximum mass for a neutron star, making it almost certainly a black hole. For decades, Cygnus X1 was the subject of debate, with some astronomers arguing it might be an unusual neutron star. But accumulating evidence, including detailed observations of the orbital dynamics and X-ray spectrum, has confirmed that it is indeed a black hole. Stephen Hawking famously bet physicist Kip Thorne in 1975 that Cygnus X1 was not a black hole. Hawking conceded the bet in 1990, acknowledging that the evidence had become overwhelming. If an entire star ventures too close, the black hole's tidal forces will stretch it vertically and compress it horizontally in a process gruesomely called spaghettification. These tidal forces arise because gravity weakens with distance. The side of the star facing the black hole experiences stronger gravity than the far side, and this difference in gravitational pull stretches the star like taffy. The star gets pulled into a long, thin stream of material, like a strand of spaghetti, hence the name. These stretched stellar fragments are then torn apart completely and absorbed into the glowing, chaotic disk. Astronomers have observed several of these tidal disruption events in recent years, catching the moment when a star wanders too close to a supermassive black hole and is destroyed. The sudden brightening as the star is ripped apart and its debris heats up creates a distinctive signature that can be detected across billions of light years. The light curve, the plot of brightness over time, shows a characteristic shape. It rises rapidly as the star is destroyed and the debris begins to form an accretion disk, then declines over months or years as the debris is gradually consumed. Different parts of the star fall back at different times, determined by their orbital energy, creating a predictable fallback rate that can be observed. Tidal disruption events are relatively rare, occurring perhaps once every 10,000 to 100,000 years per galaxy. But with modern surveys monitoring millions of galaxies, astronomers can catch a few dozen per year. Black holes are not efficient eaters, though. Not all the material falls in. Enormous magnetic fields can capture some of this matter and eject it from the black hole's poles in massive jets of particles travelling at nearly the speed of light. These jets are among the most powerful phenomena in the universe. They are powered by the rotational energy of the black hole itself and can extend for hundreds of thousands or even millions of light years, far beyond the galaxy that hosts the black hole. The jets plough through the surrounding intergalactic medium, creating enormous bubbles of hot gas and shaping the evolution of entire galaxy clusters. The mechanism that creates these jets is still not fully understood, but it involves the interaction between the black hole's spin, its magnetic field, and the swirling accretion disk. As material falls toward the black hole, it can transfer some of its energy and angular momentum to these magnetic fields, which then channel some of the material away from the black hole in focused beams. The most accepted model for jet production is the Blandford-Znajek mechanism, which extracts rotational energy from a spinning black hole via magnetic fields threading the event horizon. The energy output of these jets can exceed the combined light of all the stars in the host galaxy, making them visible across cosmological distances. Some jets produce highly energetic particles called cosmic rays that can be detected here on Earth after travelling for millions of years through intergalactic space. The final collapse of the star and the birth of the black hole also generate ripples in space-time itself, gravitational waves, which allow us to detect and study the universe's most violent events. These gravitational waves are like ripples on a pond, except the pond is the fabric of space-time and the ripples travel at the speed of light. Einstein predicted their existence more than a century ago, but they were not directly detected until 2015, when the Laser Interferometer Gravitational Wave Observatory, known as LIGO, observed the collision and merger of two black holes more than 1 billion light-years away. LIGO consists of two L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each detector has two arms, each 4 kilometers long, arranged in an L shape. Laser light travels back and forth along the arms, and the detectors measure the relative lengths of the two arms with extraordinary precision, sensitive to changes smaller than 1,000th the diameter of a proton. When a gravitational wave passes through the detector, it stretches space in one direction and compresses it in the perpendicular direction, causing the two arms to change length by slightly different amounts. By comparing the signals from the two detectors, scientists can distinguish real gravitational waves from local disturbances. Since that first detection, gravitational wave observatories have detected dozens more black hole mergers, as well as collisions between neutron stars. Each detection opens a new window into the universe, allowing us to observe events that produce little or no light but create enormous distortions in space-time. The first detection, called GW150914, came from two black holes, one about 36 times the mass of the Sun and one about 29 times the mass of the Sun, that had been spiraling together for millions or billions of years. In the final fraction of a second before they merged, they were orbiting each other at about half the speed of light. When they collided and merged, they formed a single black hole about 62 times the mass of the Sun. The missing 3 solar masses, roughly 5% of the total mass, was converted directly into gravitational wave energy, according to Einstein's equation. When two black holes spiral together and merge, they release more energy in gravitational waves than all the stars in the observable universe are emitting in light at that moment. The power output at the peak of the merger can exceed 10 to the power of 49 watts, a number so large it is difficult to comprehend. For comparison, the Sun's total power output is about 4 times 10 to the power of 26 watts. At peak merger, two colliding black holes can release energy at a rate about 10,000 trillion times greater than the Sun. The final merger happens in a fraction of a second, and the resulting gravitational wave signal sweeps upward in frequency and amplitude, creating what scientists call a chirp. The frequency increases as the black holes spiral closer together and orbit faster, then cuts off abruptly when they merge. The story we have just described, a massive star dies and leaves behind a black hole, is the traditional model. For many decades, scientists believed this was the primary way black holes formed. But recent discoveries suggest the story is not complete. The universe, it seems, has more than one way to build these cosmic monsters. Our most advanced telescopes, particularly the James Webb Space Telescope, are observing the early universe, looking back to just after its beginning. They are finding something unexpected, according to the traditional model. Supermassive black holes, millions or even billions of times more massive than our Sun, already existed when the universe was extremely young. These objects are simply too large to have formed so early. To understand why this is such a puzzle, we need to consider the timeline. The universe began with the Big Bang approximately 13.8 billion years ago. For the first few 100,000 years, the universe was too hot for atoms to form. It was filled with a dense plasma of protons, electrons, and photons, all interacting constantly. Then, as the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms in an event called recombination. The universe became transparent to light, and the photons from this era are what we observe today as the cosmic microwave background radiation. The first stars, made purely of hydrogen and helium, began forming a few 100 million years after that. These first-generation stars, called population 3 stars, have never been observed directly, but their existence is predicted by cosmological models. They formed from completely pristine gas, containing no elements heavier than lithium. Without any heavy elements, the gas could not cool as efficiently, so these first stars are thought to have been very massive, perhaps hundreds of times the mass of the Sun. They would have lived fast and died young, exploding as supernovae, or collapsing into black holes after only a few million years. If a massive star from this first generation collapsed into a black hole, it might create a black hole 10 to 100 times the mass of the Sun. That black hole could then grow by consuming gas and merging with other black holes. But there is a limit to how fast a black hole can grow. As it feeds, the infalling material heats up and radiates energy. This radiation creates an outward pressure that pushes against the infalling gas, limiting the rate at which the black hole can consume matter. This is called the Eddington limit. The Eddington limit represents the balance between the outward radiation pressure from the hot accretion disk and the inward pull of gravity. If a black hole tries to accrete matter faster than the Eddington limit allows, the radiation pressure becomes so strong that it pushes material away, limiting the accretion rate. For a spherically symmetric system accreting hydrogen, the Eddington limited accretion rate is about 1/10,000th of a solar mass per year for a 10 solar mass black hole. Even if a black hole fed continuously at the maximum possible rate, starting from 100 solar mass seed and growing for several 100 million years, it could reach perhaps a few 100,000 solar masses by the time the universe was 1 billion years old. Growing exponentially at the Eddington rate, a black hole increases its mass by a factor of about 10 every 50 million years. Starting from 100 solar masses, you get 1,000 solar masses after 50 million years, 10,000 solar masses after 100 million years, 100,000 solar masses after 150 million years, and so on. By the time 500 million years have elapsed, you might reach 10 million solar masses. By 1 billion years, you could reach 1 billion solar masses, but this requires continuous feeding at the maximum rate with no interruptions. But the James Webb Space Telescope has found supermassive black holes with billions of solar masses when the universe was less than 1 billion years old. Some of these black holes existed when the universe was only about 700 million years old. The numbers simply do not add up. A black hole born from a single star could not have grown to such enormous size in the available time. This is a major cosmic mystery. How did these giants reach such incredible sizes so quickly? This puzzle has led astronomers to seriously consider an idea that was once purely theoretical: direct collapse. In the very early universe, conditions were quite different from today. Under specific circumstances, enormous clouds of primordial gas could have collapsed all at once, bypassing star formation entirely and creating a massive seed black hole directly. Here is how it might work. In the normal process of star formation, gas clouds fragment into many smaller clumps, each of which becomes a star. The fragmentation occurs because the gas can cool efficiently, losing energy and allowing gravity to compress it into denser clumps. Cooling is aided by the presence of molecules like molecular hydrogen and heavy elements like carbon and oxygen, which can radiate energy away in the form of infrared light. But if conditions prevent fragmentation, if the gas stays relatively warm and smooth, the entire cloud could collapse as a single massive object. This requires a very specific set of circumstances. The gas must be pure hydrogen and helium with no heavier elements to help it cool and fragment. It must be bathed in ultraviolet radiation from nearby stars, which keeps it warm by dissociating molecular hydrogen. Molecular hydrogen forms when two hydrogen atoms bond together, and it is very efficient at cooling gas through molecular transitions. If ultraviolet radiation breaks apart the molecular hydrogen as fast as it forms, the gas cannot cool efficiently, and it must be dense enough that gravity can overcome the gas pressure. The gas must also be relatively smooth, without significant density fluctuations that would cause it to fragment prematurely. Under these rare conditions, a cloud containing tens of thousands or even hundreds of thousands of times the mass of the Sun could collapse directly into a black hole, bypassing the star phase entirely. The collapse would proceed on a timescale of hundreds of thousands to a few million years, much longer than a stellar core collapse, but still rapid on cosmic timescales. As the cloud collapses, it heats up, but if it cannot cool efficiently, the thermal pressure builds up and eventually halts the collapse before nuclear fusion ignites. The result is a supermassive star, or a quasi-star, an enormous object held up by radiation pressure rather than fusion. These objects would be inherently unstable and would likely collapse into a black hole within a few 100,000 years. This provides a significant head start for growing a supermassive black hole. Instead of starting with a seed black hole of 10 to 100 solar masses, you start with a seed of 10,000 to 100,000 solar masses or more. Now the numbers work. A black hole starting with this much mass, feeding steadily for several 100 million years, can reach billions of solar masses by the time the universe is 1 billion years old. For years, this remained just a hypothesis, a theoretical possibility with no observational evidence. But now, the James Webb Space Telescope is finding intriguing evidence that it might be correct. For instance, astronomers have identified objects they call little red dots in the early universe. These are compact, extremely red objects that appear in deep images taken by the James Webb Space Telescope. Their red color indicates they are either very dusty or very distant, or both. While scientists are still debating their exact nature, some models suggest these could be candidates for incredibly massive, short-lived supergiant stars on the brink of collapsing into these heavy seed black holes. These hypothetical supergiant stars, sometimes called supermassive stars, would be hundreds of thousands or millions of times more massive than the Sun, burning with such intensity that they could only survive for a few 100,000 years before collapsing. If confirmed, they would represent a population of objects unlike anything we see in the modern universe. The stars would be so massive that their cores would be dominated by radiation pressure rather than gas pressure, making them inherently unstable. Even more intriguing is a system nicknamed the Infinity Galaxy, where a supermassive black hole has been found in an unusual location situated between two colliding galaxies. In most galaxies, supermassive black holes sit at the center, where the density of stars and gas is highest. This is because supermassive black holes form from dense concentrations of gas, and the centers of galaxies are the densest regions. Finding one between two galaxies is unusual and suggestive. While not yet confirmed, one leading theory proposes that the violent collision compressed a massive amount of gas and triggered a direct collapse, forming a supermassive black hole essentially from scratch. The collision of the galaxies would create shock waves in the gas, compressing it and potentially creating the exact conditions needed for direct collapse. When two galaxies collide, their gas clouds ram into each other at high speeds, creating regions of extreme density and temperature. These shock-compressed regions could provide the perfect environment for direct collapse black hole formation. The galaxies themselves do not actually collide in the sense that the stars crash into each other. Galaxies are mostly empty space, and the stars pass by each other without colliding. But the gas clouds, which are much denser and more extended, do collide, and this collision can have dramatic effects. This does not mean we are observing the collapse in real time. Light from the Infinity Galaxy has been traveling for billions of years to reach us, so we are seeing it as it was in the distant past. The universe is about 13.8 billion years old, and light travels at a finite speed. So when we look at distant objects, we see them as they were in the past. The Infinity Galaxy, being several billion light years away, is being seen as it was several billion years ago, when the universe was much younger. But systems like this offer our best glimpses yet into what the formation of one of these heavy seed black holes might look like. As the James Webb Space Telescope continues to survey the early universe, astronomers expect to find more examples of these unusual objects, which will help confirm or refute the direct collapse hypothesis. The telescope's ability to observe in infrared light allows it to see through dust and detect objects so distant that their light has been stretched to infrared wavelengths by the expansion of the universe. Every new observation adds to our understanding and raises new questions. Some of the black holes being discovered are even more massive than expected, suggesting that either direct collapse was even more efficient than thought, or that multiple formation mechanisms operated simultaneously. There may be other pathways as well. Some theories propose that dense star clusters in the early universe could merge together to form intermediate mass black holes, which then serve as seeds for supermassive black holes. In a dense star cluster, stars can collide and merge, building up more massive stars over time. Eventually, the most massive star in the cluster might reach hundreds of solar masses and collapse into a black hole. This black hole could then continue to grow by consuming other stars in the cluster and by merging with other black holes formed in the cluster. The resulting intermediate mass black hole, perhaps a few thousand solar masses, could serve as a seed for a supermassive black hole. Others suggest that the first generation of stars, made of pure hydrogen and helium, might have been much more massive than typical stars today, potentially creating heavier seed black holes when they collapsed. Population 3 stars, the first stars in the universe, are predicted to have been more massive than later generations of stars because the gas from which they formed could not cool as efficiently. Without heavy elements to radiate energy away, the gas remained warmer and more diffuse, and larger masses were needed for gravity to overcome the gas pressure and cause collapse. Some models predict population 3 stars could reach hundreds or even thousands of solar masses, far more massive than any star observed in the modern universe. When these giants died, they might have left behind black holes of hundreds of solar masses, providing heavier seeds than the tens of solar masses left by modern massive stars. The early universe was a strange and turbulent place, with physical conditions very different from what we observe today. The density of matter was much higher, galaxies were smaller and closer together, collisions and mergers were frequent, and gas clouds had not yet been enriched with heavy elements. It is entirely possible that multiple pathways operated simultaneously. Some black holes might have formed from the collapse of massive population 3 stars, others from direct collapse of gas clouds, and still others from runaway collisions in dense star clusters. The supermassive black holes we see today at the centers of galaxies may represent a mixture of different formation channels, all contributing to the final population. These new discoveries do not invalidate the story of stellar collapse. They simply add another fascinating chapter to our understanding. They reveal that the universe has more than one path to creating these cosmic giants. The stellar collapse pathway, where individual massive stars explode as supernovae and leave behind black holes, continues to create black holes today. We observe supernova explosions in nearby galaxies regularly, and gravitational wave observatories detect the mergers of stellar mass black holes that form this way. But in the early universe, direct collapse and other exotic processes may have been equally or even more important. Understanding which formation mechanism dominates under which conditions is one of the key questions driving current research. From a star's first fusion reactions to its final, crushing collapse, we have witnessed one of nature's most extreme transformations. We watched a star forge the building blocks of life, only to have its nuclear fire extinguished, triggering an implosion that creates a black hole, an object powerful enough to shred other stars and warp the fundamental fabric of reality itself. The death of a star is not merely an ending. It is a transformative event that enriches the universe with new elements and creates gravitational powerhouses that will shape galaxies for billions of years into the future. The carbon, nitrogen, and oxygen scattered by the supernova will eventually become part of new stars, new planets, and perhaps new life. The elements your body is made of pass through this cycle at least once, and probably multiple times. The iron in your blood was forged in the core of a massive star and scattered into space by a supernova explosion. The calcium in your bones, the sodium and potassium that allow your neurons to fire, the phosphorus in your DNA, all came from stars that died billions of years ago. You are the universe made conscious, stardust contemplating its origins. The black hole left behind will continue to influence its surroundings for as long as the universe exists. If the black hole resides at the center of a galaxy, it will regulate star formation, control the flow of gas, and determine the ultimate fate of that galaxy. Supermassive black holes appear to co-evolve with their host galaxies, growing in tandem with the galaxy's stellar population. There is a tight correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the central concentration of stars. This suggests that the black hole and the galaxy influence each other's growth, though the exact mechanisms are still being researched. Black holes grow over time through accretion and mergers. As they consume more gas and dust, or as they collide and merge with other black holes, they increase in mass. The supermassive black holes at the centers of galaxies, millions or billions of times the mass of the Sun, are thought to have grown from smaller seed black holes through this process, accumulating mass over billions of years. Our own Milky Way galaxy harbors a supermassive black hole called Sagittarius A star at its center, with a mass of about 4 million times the mass of the Sun. In 2020, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the glowing ring of hot gas orbiting the black hole. Eventually, in the unimaginably distant future, when the last stars have faded and the universe has grown cold and dark, black holes may be the only objects still actively shaping the cosmos. The universe is expanding, and the expansion is accelerating due to dark energy. In trillions of years, all the galaxies outside our local group will have receded beyond the cosmic horizon, unreachable even by light. Star formation will cease as the supply of gas is exhausted. Existing stars will burn out and cool, leaving behind white dwarfs, neutron stars, and black holes. In about 10 to the power of 100 years, even black holes will evaporate through a quantum process called Hawking radiation, over timescales that dwarf the current age of the universe. Hawking radiation is a purely quantum mechanical effect that occurs at the event horizon. Quantum mechanics predicts that empty space is not truly empty, but is filled with virtual particle-antiparticle pairs that constantly pop into existence and annihilate each other. Near the event horizon of a black hole, these pairs can be separated by tidal forces, with one particle falling into the black hole and the other escaping to infinity. From the perspective of a distant observer, the black hole appears to emit radiation, slowly losing mass and energy. The rate of Hawking radiation is inversely proportional to the mass of the black hole, so larger black holes evaporate more slowly. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate completely. A supermassive black hole might take 10 to the power of 100 years or longer. These timescales are so vast that they make the current age of the universe, a mere 14 billion years, seem like an instant. We are only beginning to grasp these cosmic mysteries. Every new observation, every new gravitational wave detection, every new image from our most powerful telescopes adds another piece to the puzzle. We have learned that black holes come in a range of sizes, from stellar mass black holes created by collapsing stars to supermassive black holes at the centers of galaxies. We have discovered that they are not rare cosmic oddities, but common features of the universe. Most galaxies, including our own Milky Way, harbor a supermassive black hole at their center. We have found that black holes can merge, creating even larger black holes and sending ripples through space-time that we can detect from billions of light years away. The detection of gravitational waves has opened an entirely new way of observing the universe. Before gravitational wave astronomy, we could only learn about the cosmos by studying electromagnetic radiation, light in all its forms, from radio waves to gamma rays. Now we can listen to the space-time vibrations caused by colliding black holes and neutron stars. This is analogous to the difference between watching a silent movie and watching a movie with sound. Gravitational waves provide complementary information that cannot be obtained any other way. They tell us about the masses and spins of the merging objects, the dynamics of the merger, and properties of space-time itself. But many questions remain unanswered. What exactly happens at the singularity, where density becomes infinite and our equations break down? Current physics cannot describe the singularity because general relativity predicts that space-time curvature becomes infinite there, and quantum mechanics cannot be ignored at such small scales. We need a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics to understand what truly happens at the center of a black hole. String theory, loop quantum gravity, and other approaches are attempting to construct such a theory, but none have been confirmed experimentally. How do supermassive black holes grow so quickly in the early universe? As we have discussed, direct collapse may be part of the answer, but many details remain unclear. What role do black holes play in the evolution of galaxies? We know that supermassive black holes can influence star formation through their jets and radiation, heating the gas and preventing it from cooling and collapsing. This feedback is thought to explain why the most massive galaxies are not still forming stars rapidly. But the details of how this feedback operates are still being worked out through observations and simulations. Can information that falls into a black hole ever escape, or is it lost forever? This is the black hole information paradox, one of the deepest problems in theoretical physics. Quantum mechanics says that information cannot be destroyed, but general relativity seems to say that anything that falls into a black hole is lost forever when the black hole eventually evaporates. Hawking radiation carries away energy, but appears to carry no information about what fell in. This contradiction between quantum mechanics and general relativity suggests that our understanding of one or both theories is incomplete. Recent work suggests that information might be encoded in subtle correlations in the Hawking radiation or on the event horizon itself, but the issue is not yet resolved. These are some of the deepest questions in modern physics and astronomy, and answering them will require new observations, new theories, and perhaps even a new understanding of the fundamental laws of nature. The field of black hole physics sits at the intersection of general relativity, quantum mechanics, thermodynamics, and information theory. Progress requires insights from all these areas, and breakthroughs in one area often lead to advances in others. What other secrets are hidden out there in the darkness? The search for answers continues. Every night, telescopes around the world and in space scan the skies, looking for the telltale signs of black holes. Gravitational wave observatories listen for the space-time ripples created by merging black holes. Gravitational wave astronomy is still in its infancy, and future detectors will be even more sensitive. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will be a space-based gravitational wave observatory capable of detecting supermassive black hole mergers across the entire observable universe. The Einstein Telescope and Cosmic Explorer are planned next-generation ground-based detectors that will be 10 times more sensitive than current detectors. Supercomputers run simulations to model the complex physics of accretion disks and jets. These simulations solve the equations of general relativistic magnetohydrodynamics, tracking how gas and magnetic fields behave in the curved spacetime near a black hole. The simulations can take months to run, even on the fastest supercomputers, but they reveal details that cannot be observed directly. They show how magnetic fields get twisted and amplified, how jets are launched and collimated, and how the disk structure changes over time. And theorists work to reconcile general relativity with quantum mechanics, seeking a theory that can describe what happens inside a black hole. This is one of the great quests of modern physics. The search for a theory of everything that can unify all the fundamental forces and explain all physical phenomena, from the smallest subatomic scales to the largest cosmic scales. Black holes sit at the frontier of this quest because they bring together gravity, quantum mechanics, and thermodynamics in ways that expose the limitations of our current theories. The quest to understand these enigmatic objects is one of the great adventures of modern science, and we are living in a golden age of discovery. In the past decade, we have detected gravitational waves, imaged the shadows of black holes with the Event Horizon Telescope, discovered supermassive black holes in the infant universe with the James Webb Space Telescope, and observed tidal disruption events as they happen. Each of these breakthroughs was considered science fiction just decades ago. Now they are routine observations, pushing the boundaries of our knowledge further than ever before. The journey from understanding how stars die to probing the nature of space-time itself has been one of the great intellectual achievements of humanity. It required the combined efforts of thousands of scientists across centuries, building on each other's work, testing theories against observations, and constantly refining our understanding. From the theoretical work of Einstein and Oppenheimer to the observational breakthroughs of modern telescopes and gravitational wave detectors, each step has brought us closer to comprehending some of the most extreme phenomena in nature. Black holes remind us of how much we have learned and how much remains to be discovered. They are laboratories for testing physics under the most extreme conditions imaginable, natural experiments that we could never create artificially. They challenge our understanding of space, time, matter, and information. They are simultaneously the simplest objects in the universe, described completely by just their mass, spin, and electric charge, and the most mysterious, hiding their interiors behind event horizons that we can never see past. If you found this exploration to the edge of reality fascinating, be sure to subscribe for more journeys into the cosmos. Thanks for watching.